Hello and welcome everyone to another episode of Embedded TV, where we'll learn embedded systems together. Today we're going to be looking at some C code, and I'm going to be walking you through and explaining to you what exactly is going on. So this is a perfect way for you to learn C and understand it better from practical examples. So today we're going to be looking at the flash chip driver in Linux, which is written in C, of course. Let's get started. I'm just going to switch screen and let's go here. So what do we have here? I've taken screenshots of the driver at different places, and also I've taken screenshots of some other code that's going to run as part of the SPI driver, but we're going to be looking through this in order. So first of all, if we look at the typical flash driver, so what does this driver do exactly? Well, we have chips that contain data. They're flash chips. And these chips are connected over SPI to a Linux computer. SPI is the serial protocol that these chips are talking. So they have 4 lines. They have clock, clock, signal. They have MISO, master in, slave out, and MOSI, master out, slave in, and then they have MOSI should be there. Let's see, MOSI, and then they have a chip select signal. So using these 4 signals, the chip can communicate with the Linux computer, and the Linux computer will basically send a bunch of clock cycles, and then it will send master out, slave in on this. This is the outgoing signal to the chip. It will send a command. Maybe it will tell the chip to read data at a specific address, and then the chip will reply on the master in, slave out, while the master is clocking the signal here. So this is SPI. Now, the driver is structured as follows. So we're going to look through this code and look at some good practices here. So the entry to this code is actually over here. So the entry to this code is the probe function. Let's make this red. And when the Linux driver subsystem encounters any driver that let me just explain real quick here. So when the Linux kernel is booting, it's parsing a device tree. And in the device tree, you can have different sections where we, for example, can have a section that we call flash, and we then write compatible, and set it to string, for example, JEDEC SPI NOR. And when the system is parsing this section, it's actually going to check the compatible string, and there are a whole bunch of different compatible strings with which this particular driver is compatible, but this one is the generic one. So this one is set by default. So we define this table as static const, which means that static means it's visible only in current file. Const means that it's not going to change, which means also that it's not going to be placed into the data section where the data can be changed. It will be just a constant placed directly in the firmware. Now, let's see. Or it will be placed in the read-only section, for example, where the data is designed not to be read. Then we define the struct open firmware device ID, and this table then contains a series of compatible strings. There are more of them higher up in this file, but the default one is here. And then we use a macro to to define this table. I'm not going to go into details about this macro. Let's just focus on the driver itself. So we define the driver as static once again, so it's only visible in this file, struct SPI driver. And this structure has a few fields here. First of all, we set the name. We have the match table, which we set to this table here, which is then used to match the driver with the particular chip, with a particular node in the device tree. And then we have probe and remove. And whenever the device tree node is encountered, the probe method is going to be called for that particular node. So the purpose of the probe is to instantiate device. So to instantiate a device instance, and you can have multiple instances of the same device, of course, but each device tree node will be basically connected to one device tree instance. It will be created. And then we can go directly to the probe method. In the first file here, the only interesting thing is the definition of the structure. This is the instance that's going to be created. So when probe is called, it's going to create, allocate this instance, initialize the device, and then register it with the SPI subsystem. And notice that all of this is defined in the C file. So this information is not available anywhere outside of the of this module. And in order to make that possible, we have to allocate things dynamically, specifically inside this module, and then register them with the subsystem. So let's go to the probe method and see what it does. So we have now we have the device tree node, and it's compatible. Now the probe method is called. The purpose of the probe method is to see if we can actually initialize the device. If the device cannot be initialized, then the probe method is not going to register an instance of this device with the memory subsystem in this case, actually, because we are creating an MTD device, memory technology device. So we create our placeholder for the pointer for this instance. This would be our instance, and we create a few other variables here. This is going to denote the NOR, the SPI device. This is going to be the hardware capabilities of that device, which is going to be configured specifically for this functionality that is required by this chip. And first of all, and here we are being passed an SPI device. So this probe will be called from the SPI subsystem. So it already will have an SPI device, which is to which this flash is connected, and it will be passed in here. So first thing we do here, we get the platform data, and this is done by accessing the member of the SPI object, and then we allocate our instance of the memory chip. So we call devm kz malloc. Let me actually increase this like this. What this does is it allocates the memory as part of this particular instance. So it's going to be deallocated automatically. So we can do a lot of different allocations, and then we could call just a single deallocation to deallocate all the memory associated with this driver. So this is actually allocated and associated with the SPI device. If we cannot allocate this, then we return the errno code of eNoMem. This is a common way of handling errors in C. We'll just return them as an integer. So you define your functions as an integer, and you return a negative number to signal an error, and you return 0 to signal success, which basically means no error. Now, we then set all the capabilities. So this gets configured. This gets configured to the settings that are, let's see. Yeah, this actually gets configured with the methods to read and write this memory device, and it's actually reusing functionality from the SPI NOR interface, which is a generic interface for this type of memory devices. Because keep in mind that there's a lot of different chips, and there's a lot of different types of devices, and you don't want to duplicate that in every single driver. So in this specific driver, you just keep the most driver specific code, and then you have the this is basically like subclassing, and then you defer the other functionality to more generic code. So here we set function pointers for reading, writing, writing register, and reading a register, and this will be called by the generic code whenever it needs to read or write a register to and from this flash memory. And then we set this flash object as data for the SPI device, which we were passed the generic SPI. This is like a generic SPI device, and we save this so that we can retrieve this later in the other functions. So then we can just get this data by calling SPI get DRV data, and we'll get the flash object, the one that we have allocated here, which is our private. This is the private object that is specific for this driver. Then we go here, and this more hardware settings, and then we set the name, further configure this, and then we scan. I haven't taken a screenshot of this function, but I think what this does, I may be wrong here. I think what this does is basically it scans for the device based on capabilities, and then if that scan fails, then we return. But if it doesn't fail, then we register the MTD device. Now, what I find a little bit strange is that it didn't deallocate the flash object here. So it's quite possible that it's not necessary to deallocate it here, because if this function returns an error, then the device object will actually be deallocated by the SPI subsystem. And then we don't have to worry about deallocating individual objects. If everything goes well, it calls MTD device register with this NOR with the MTD where we have set the name. We have set we initialized this structure with read, write, write reg, read reg. So this will be the interface to our specific device, which represents the M25 series of chips, M25 P8 in this particular case. And once this is registered, then other parts of the code, other drivers can query this for this device and get a generic interface to this device. So they can then call SPI NOR read, and that subsystem will then call our function pointers, which implement specific functionality. So this is a typical example in C of how you do abstract polymorphism, where you can have the same where you can have the same interface to many different implementations of a specific type of object. Once this is registered, the probe function exits and the initialization continues. So this is typically you typically see, and if you print any messages in this place in the code, you will see them during the boot time before you actually get to the console. So this is when all of the devices are initialized. Now, so we can place file systems. We can place we can make this device. We can make this flash device the base device through which other protocols can save their data. But this is on the lowest level. So here we're just concerned about writing to specific addresses in the flash memory. If a file system would be using this device, it would probably go through an MTD drive, specific, so that it will probably go through a driver that makes sure that we don't get any that we don't get too much wear and tear on the flash, so we don't write to the same addresses too often and things like that. So there's a lot of things that can be built up upon this basic NOR flash device. And whenever the higher level code needs to read something, then the function pointer to this method will be called, and to it the subsystem that is managing this device is going to pass the pointer to the SPI NOR object. And then we get so remember, we set this as priv data. So we set this over here, set driver data, flash, and we retrieve this here again. This should probably use a getter method. But in this case, the choice is to just retrieve it directly. And then we have the SPI device through which we're going to be communicating, and we create 3 transfers, and we create a message for this transaction of the read transaction. And it's actually pretty smart to separate the SPI into transfers, because now you can have multiple different operations that you just chain together, and then you execute them all at the same time. So it's very it's much easier to do it than if the API was just taking a buffer and just writing just writing to the SPI port. Because think about it, the SPI port is actually writing first and then it's reading. So it's always this dual operation, even though you're still reading when you're writing. So if we go back here to the SPI, to how it was working. So the clock starts clocking, and then we output data to the master out slave in, and then we read data from master and slave out. But we're also reading data essentially here as well. It's just that we discard this data. We don't care about it because we're writing at the same time. But the device could send data right away. It depends what kind of device it is. But basically, it's a duplex operation. SPI bus is a duplex bus, so you can both write and read at the same time. But depending on which device it is, you would have to do it differently. And so transfers allow this functionality to happen. You can have a write transfer, and then you can have a read transfer, and you just execute them as the same operation, which makes it very practical. So first we check if read is supported. If it is supported, then we initialize the flash read message, and we just do an SPI flash read. So that's simple. And then we return the read length. But if this is not supported, then we do all of this manually. So we go SPI message init, I think this is probably dependent, whether read is supported is probably dependent on the driver. If this type of operation is supported. If this is not supported, if SPI flash read is not supported, then we initialize the message and go ahead and initialize the commands, set the address, set the TX buffer, set the length of the transmission and the total length of the transfer there, and then we add this message to the. So then we add the transfer to the message. I find it really annoying that the notation in Linux is like this. So you're acting on SPI message, so you're acting on this object, yet the argument is passed first. This is the same thing is done with lists as well, and it gets really confusing because you kind of would expect it to be such that you have a function and then the first argument would be the object on which it operates, and then you will have all the arguments. But in Linux they use this in many different places, this notation. So you're acting actually on the message, but the first argument is the thing you're adding to the message. So we have SPI message there. Then the remaining transfers are set, and let's see. Split the opcode and address into 2 transfers if needed. So I'm not really sure why it's doing this, and why it needs to, when it can be needed. But this is how the implementation has been done for this chip. And once we're done, we just we send the SPI. We add the last transaction to the message, and then we do SPI sync. And this is this then calls the SPI driver, and the SPI driver then executes the transactions as part of the SPI driver implementation. So we'll probably end up in something like this: SPI sync, and we have the transfer, and then we basically just send the transfer. Trace SPI message submit. So SPI message submit is submitting this message. And spin lock RQ safe basically disables interrupts on this core while other cores can be running, but the guarantee here is that this code will not be executed by 2 cores at the same time, or for that matter 2 threads at the same time. This is completely exclusive section in the code. And then there is more tests here, and I suppose this is probably, if we can do this operation right away, then we can just get the messages right away, and then it waits for completion on this done. Let's see what is done here. We have the context. We set the message context done, and done is actually a completion declared on stack. So when the messages have been sent, so now we are waiting. So we put this thread to sleep, or whoever was calling this code through a system call, for example. So this code goes to sleep. Not necessarily, but if the transfer cannot be completed right away, it will go to sleep. And then the actual transfer can happen in a different thread or on a different core, and several transfer can actually happen at the same time on different interfaces using the same code. So it's really interesting to look at how Linux is designed, because you really see those very good design techniques where they really pay great attention to how code is written so that it's completely thread safe and doesn't create unexpected results if multiple processes call the same code at the same time. And this is also apparent by the fact that we are always using objects or structs to store all data. So all functions operate on structs. There is never any global variables unless they're const and static. So that's it. This was a short introduction, or maybe should you call it like a short explanation of how the Flash driver is written in C in Linux. I hope you found it interesting, and I'll see you in the next video. Thanks for watching.